Good morning and welcome back to math. Today we're going to take a look at the practice problems. Just let me adjust this a bit. There we go. Today we're going to look at the practice problems for 8.3, and that is all about solving systems using the process of elimination. So recall that you've already looked at two ways of solving systems. One of them is graphically, either graphing on a grid or using your graphing calculator. And the second type was solving by substitution, where you isolate one of the variables, plug the expression into your other equation, and eventually solve to get your solution. Solving by elimination, I have already posted a lesson on that, but very quickly, excuse me, very quickly, when you're solving a system by elimination, you're looking at making one of the terms same in both equations and then adding or subtracting to eliminate that term. Then you isolate your remaining term, and finally substitute that term, and that allows you to solve for your second term. Okay? The way that this particular practice session sets itself up is, to my mind, a little bit backwards. Questions 1 and 2 should really be done after we do questions 3 and 4. So that's what we're going to do. Okay? So we'll go down to question 3. Just for some practice, I'm going to leave this on the sides just so that you can see we're going through the steps. So what we've got here is a very simple system of equations. You have two equations, and when you take a look at this, you can see that we have the same term using the variable a. And when I say the same term, what I'm basically saying is you have the same coefficient in front of that term, okay? So in this case, a is the term that's the same because each of these has a coefficient of 1, okay? And given that, we don't have to do step 1, we don't have to manipulate the terms in any way through multiplication to make them the same. They're already there, okay? And so we can proceed right to the next step, which is add or subtract to eliminate the term. Now remember, if the sign on our terms is the same, that means the operation we're going to perform is subtraction, and you'll see why in a second. Notice also, these terms are lined up with like terms one beneath the other, okay? So we've got a coefficient, 52 and 70. We've got an a variable, the equal sign, and your b variable. You'll see that they all line up. That's very important because it makes it less confusing when you go to that second step, which in this case is subtraction. Okay, so we're going to subtract each of these terms from the one above it. So 52 minus 70 will give us negative 18. Negative a minus negative a, remember this double negative is like saying negative a plus a, and negative a plus a will give you 0a. Okay, 1 minus 1 is 0. Equals, just bring the equal sign down, and then 4b minus 6b gives you negative 2b. Okay? Now we know that this 0a just cancels. I'm just going to write this more simply as negative 18 equals negative 2b, and then it becomes pretty obvious that our last step to isolate b is to get rid of that negative 2, divide both sides by negative 2, and that gives you 9 equals b. Okay? We're halfway there. Remember that our solution will eventually be an ordered pair. I'll just put these in alphabetical order, so b is our second term, and there it is. Okay? Once you have a value of one of your variables, take that value, plug it into either one of your two equations, and solve for your unknown variable. So from this point on, it's kind of like substitution because you're substituting the value of this variable. So we're saying b equals 9. I'm just going to use the first equation. So 52 minus a equals 4 times. I'm going to sub the value 9 where I see b, so it becomes 4 times 9. And then I'm going to simplify and isolate the variable. So 52 minus a equals 4 times 9 is 36. I want to isolate a, so I'm going to subtract 52 from both sides. 52 minus 52 will give me 0, leaving me with negative a on the left. 36 minus 52 will give me negative 16. Okay? Finally, we don't want that negative sign there, so we know how to get rid of that. We can multiply everything through by negative 1. Negative 1 times negative a is positive a. Negative 1 times negative 16 is positive 16. That gives us our second variable. And now, because it's asked us to, and we'll do it this time, but I'm not going to verify every single one. Verification is a fairly straightforward process. So, to verify the solution, remember, we take our values for a and for b, we sub them back into our equation, and then we check to see if the left side equals the right side. So, for our first one here, I'm just going to use this because I'm running out of room. So, we said that a equals 16. So, our equation then, our 52 minus a equals 4b, becomes 52 minus 16, that's our value of a, equals 4 times 9. 52 minus 16 equals 36, and 52 minus 16 does equal 36, so left side equals right side. We're good. Now, you can't stop there, okay? When you verify, you have to do it with both equations. So, we'll do it with the second equation very quickly. 70 minus a equals 6b becomes 70 minus 16 equals 6 times 9. Simplify. 70 minus 16 equals 6 times 9 is 54. And 70 minus 16 does equal 54. So again, left side equals right side. Okay, so we verified. We know that for both equations, the solution works, and so indeed, that solution is the point of intersection, that one point where the two lines cross. Okay, so having done this example, let's go back now and take a look at numbers 1 and 2. Okay, now that we've refreshed our memory as to what elimination actually is. Question number 1 says, use the following example to explain why the order of subtraction is not important when solving systems of equation by elimination. So, what they've done here is they have two equations. They're the same two equations in each case. It's just that they're in a different order. In this one, the 5x plus 9y equals 7 is on top. On this one, the 5x plus 9y equals 7 is on the bottom. So your order of subtraction is different. Now, typically, when you very first, were subtracting, you were taught that the order is very important when you're subtracting. And the reason the order was important then is because depending on the order that you subtract, you'll get either a positive or a negative answer. In this case, it doesn't matter because of the last step in isolation. In this case, you would have said, well, I don't need this 0y, so I have x equals 18. That's my value for x in this particular system of equations. In this system of equations, again, getting rid of that 0y, you get negative x equals negative 18, and all that means is, to isolate x in this one, you just have to do that one more step, right? Because we want to get rid of this negative sign, so we will multiply the whole mess through by -1, and that will give us exactly the same answer that we had in our second system of equations. So, the reason order is not important is because when we isolate, if there's a negative sign attached to the variable, we get rid of it anyways. So we end up with the same answer. The order isn't important. For this next one, it says, the subtraction of two equations is shown. Explain why this subtraction is not useful for solving the linear system 5x plus 3y minus 1 equals 0 and 2x minus y plus 4 equals 0, and it has to do with this second step here. If you're solving by elimination, what you hope to do in step 2 is through addition, or in this case, subtraction, you hope to eliminate one term. Now, take a look at the answer. We haven't eliminated a term. So, why is this not useful? As neither the x nor y terms have the same coefficient, remember the coefficient is just the number in front, we haven't eliminated a variable. And since we haven't eliminated a variable, we can't proceed to the third step, which is to isolate the remaining term. We can't isolate it because there's still two separate variables involved. In order to solve this system using elimination, what we would have had to do is multiply the second equation by 3. You'll notice if we had multiplied the second equation by 3, and we'll do this just to show you what I'm talking about. Had we multiplied the second equation by 3, what we would have ended up with, and I'm just going to copy this one out, 5x plus 3y minus 1 equals 0. This second equation would have become 3 times 2 is 6x, 3 times minus y is minus 3y, 3 times 4 is 12, and 3 times 0 is 0. Now you'll see that what we've got is we've made the coefficient of y the same number. There's a 3 in front of y or attached to y in both cases. And so in this instance, because the signs on the 3y are different, one is plus, one is minus, in this case, we would add these two equations, resulting in 5x plus 6x, 11x, 3y and negative 3y gives us 0y. Negative 1 plus 12 would give us 11, and 0 plus 0 is obviously 0. That eliminates that term, giving you 11x plus 11 equals 0, and eventually isolating to 11x equals negative 11, subtract 11 from both sides, x equals negative 1 after dividing both sides by 11. And now we have a value for x, we can sub it into our second equation, and we can get a solution. But until we manipulate this equation, elimination doesn't work. Okay? So again, a little confusing for those first two questions if you haven't had some practice with these other ones. Okay? Maybe we'll do one more of these. This one, and this. Let's do C. C is just a little bit trickier because the two equations they've given you are not written in such a way that the variable terms fall beneath each other. Okay? So, what we need to do is we need to get, and we're going to manipulate the second equation. We want to get it so that it looks like the first one, with the x on the left and the constant term and the y on the right. So we can just add and subtract terms to move them around. Okay? To get the x on the left, we simply add 6x to both sides. That will give us 8y plus 6x equals negative 9. Okay, we're partway there. We want it to look like this one up top, so that means now we have to move the y over to the other side. So we'll just take away y from take away 8y from both sides, and that eventually gives us 6x equals negative 9 minus 8y. And you can see now we've got it in the same format as your first equation. The x term, the equal sign, the constant term, and the y. Okay? So I'm going to rewrite this as 7x equals 11 plus 5y, my first equation. My second rearranged equation, 6x equals negative 9 minus 8y. And now I have everything lining up. Okay? I'm still not done. I decided to do this one because it is a bit of a pain. There's a lot of manipulating to do. So you'll notice that neither of these terms has the proper coefficient attached. So now we're going to have to manipulate both equations so that we can either make the coefficient of x the same or the coefficient of y the same. And I'm going to make the coefficient of x the same. So the least common multiple of 7 and 6 would be 42. That means we're going to have to multiply the top one by 6, that will give us a 42, and the bottom one by 7, and you'll see that when we carry out the multiplication, 6 times 7 is 42x, equals 6 times 11 is 66, 6 times 5 is plus 30y. The one below becomes 7 times 6 is 42x. Notice we've made the coefficient of x the same now. 7 times minus 9 is minus 63. 7 times minus 8 is minus 56y. Now we have the coefficient of x the same. Since they're both positive, when we manipulate them for elimination, we have to subtract. Okay? 42 minus 42 will give us 0x. 66 minus negative 63 is like saying 66 plus 63. That'll give us 129. 30 minus negative 56 is like saying 30 plus 56. That will give us 86y. Okay? This one's not going to be very nice. Oh well. So, isolate y. Subtract 129 from both sides. That'll give us negative 129 on this side and 86y on this side. Divide both sides through by 86. That will give us y on this side. I'm going to get my calculator because that is too large a number to simplify for Monday morning. So, give me a second. And it simplifies actually quite nicely to 1.5. Remember, you're okay with using decimal values so long as they're terminating decimals. You can't take a repeating decimal and round it. It won't give you the exact answer. Okay? So, because this terminates, gives us 1.5, we can go with that. And we now know that the y part of our solution is 1.5. Okay? So, we've made the terms the same. We've, in this case, subtracted to eliminate that x term. We've isolated that term. We know what y equals. Last step, substitute. So, we're going to substitute that value of 1.5 into one of our original equations, and we'll use the first one. So we get 7x equals 11 plus 5 times y, or in this case, 5 times 1.5. Simplify. 7x equals 11 plus 7.5. 7x equals 18.5. And finally, divide through by 7, giving us x equals, and again, excuse me while I ask Mr. Calculator. And that gives us a not so friendly answer of 37/14. For our answer. Okay? And we can just plug it in up here. 37/14. Now, that looks ugly, and you might want to verify this just to make sure it's correct. Okay? But we're going to move on right now because I want to try and keep these lessons to under a half an hour. Okay? So, this one, number 4, says, attempt to solve the following systems of equations. How is each pair of lines related? Okay, so we've got our two lines. The coefficient of x or the coefficient of y are not the same coefficient, so we have to manipulate it. I'm going to make the x the same. Okay, so I'm going to multiply this equation through by 4. That will give me 4 times x is 4x. 4 times 3 is 12y. 4 times 11 is 44. I'll write my second equation underneath it, and you immediately notice, what the heck? It's exactly the same equation. So, let's see if we can solve it anyways. We're going to isolate x, and because the sign on the x term is the same, we know we have to subtract. And what do we get? 4x minus 4x is 0x. 12y minus 12y is 0y. 44 minus 44 is 0. Does not work. Well, if you were to graph these two lines, what would you notice? Well, because they're exactly the same equation, what you would notice is that, what you would notice is that if the first line looked like this, I'm just going to use a squiggly line to differentiate. The second line would look exactly the same. Okay? That shouldn't be a surprise. They're exactly the same equation. So, how is this pair of lines related? These lines are coincident. Again, a fancy math term simply meaning they are exactly the same. And since they're exactly the same, your solution is going to be infinite, right? Because there are an infinite number of points where these two lines intersect. They're right on top of each other. So every point on one line will also be a point on the other line. So these lines are coincident, or the same. So we can't solve a system of coincident lines using elimination, or substitution for that matter, because there's an infinite number of solutions. Let's take a look at the next one. So for the next one, again, we can either make the coefficient of x the same or the coefficient of y the same. I'm going to make the coefficients of x the same. What that means is we're going to have to multiply the top by 3, right? That'll give us 6x. And the bottom by 2, also giving us 6x, resulting in the following equations. 3 times 2 is 6x. 3 times minus 6 is minus 18y. 3 times 9 is 27. For the second one, 2 times 3 is 6x. 2 times minus 9y is minus 18y. 2 times 12 is 24. Now, when we go to subtract, which we have to do because remember the sign on 6x is the same, they're both positive. So when we go to subtract, we get 6x minus 6x, 0x. Negative 18y minus negative 18y is like saying negative 18y plus 18y gives us 0y. Looks like the one we just did until you get to the constant term. 27 minus 24 gives us 3. This is not the same. Okay? Not the same as the last example because everything doesn't disappear. If you were to graph these two lines, you would get something that looks like this, where one line is like that, the other line is like that. So, this indicates that we have a different y-intercept. Remember, when you put these terms into slope-intercept form, y equals mx plus b, the b term, the constant term, is your y-intercept, and our y-intercepts are different. So, when the variables are both 0, but there are different constant terms, you have parallel lines and since they're parallel, they never meet. They never intersect. Remember we looked at this in lesson 8.1. And if they never intersect, therefore, no solution, because they never intersect. They don't share any x or y values. Okay? That's it for today's lesson. I hope it was useful. Tomorrow we'll maybe take a look at some word problems, because I think those are where you will have the greatest challenge with this chapter. Anyways, have a lovely rest of your day. We will see you again.